Hi everyone. In sections 5.4 and 5.5, you will need to be able to know or figure out 19 identities and be able to use 8 more once you see them. So 19 plus 8, in a way, 27 more. In fact, you should be able to recognize pieces of these identities over here so that you can recognize when you can apply them and realize, hey, I might be able to use an identity here. So you should be familiar with the various pieces in here. Ideally, you would memorize them, but it also helps to be able to figure them out. And also, it helps to recognize various pieces in here. So let's start applying these identities. First off, we can do things like find the exact value of something like sine of 15 degrees. Because we can rewrite 15 degrees in terms of other known special angles. In many of these problems, it may be easier to work in terms of degrees. You could use radians, but remember that it's sometimes hard to apply arithmetic to radian measures, like pi over 4 or pi over 3. Students often have a hard time adding or subtracting fractions with pi in them. I hope you can do that, but you may find that in many of these problems, it will be easier to work in degree measure, like 15 degrees. Okay, so how can we rewrite or re-express 15 degrees in terms of other known special angles? There are actually infinitely many ways to relate this 15 degrees to known special angles, but what are a couple of ways that we can rewrite 15 degrees in terms of known special angles? Well, let's see. 15 degrees is equal to how many degrees minus how many degrees. There are infinitely many pairs of responses you could give, but 15 degrees is equal to how many degrees minus how many degrees. What would be some simple responses here? Well, again, there are infinitely many possible choices you could make, but you could say 15 degrees is equal to 45 degrees minus 30 degrees. You could also do, for example, 60 degrees minus 45 degrees, but let's go ahead and run with this. Which implies that we might be able to use a difference identity because of the subtraction there. So we're going to express sine of 15 degrees as sine of the quantity 45 degrees minus 30 degrees, this difference of two special angles. Now remember, does this equal sine of 45 degrees minus sine of 30 degrees? And the answer is nope. Cross this out. In fact, I'm going to erase it. That's wrong. We do not have what we call linearity here, or we don't have a distributive property here. Remember, there's an actual difference identity. That's more complicated than that. It might help to perform a substitution. You could do this mentally. We could let we could let 45 degrees be u, let 30 degrees be v. And from the handout we got earlier, well, by now, I hope you know this, but sine of u minus v is equal to, I'll put in some parentheses to make this clearer, sine of u times cosine of v minus cosine of u times sine of v. Remember, the sum identity was the sum of the mixed up products. The difference identity means that we switch the plus sign here to a minus sign. So let's apply this difference identity. Again, sine of u minus v equals sine of u, 45 degrees, times cosine of v, 30 degrees, minus cosine of u, 45 degrees, sine of v, 30 degrees. And hopefully you won't need a calculator for these. In fact, you should write down exact values anyway. What was the deal for the 45 degree angle? Well, both the sine and the cosine values were root 2 over 2. Those were the coordinates of that intersection point. Both the cosine value and the sine value for the 45-degree angle will be root 2 over 2. That's for 45 degrees. And for 30 degrees, you could get this from a table that you've mind dumped on your test, like on the back of the test. 30 degrees, that was the sort of flattish angle. Not that flat. 30 degrees was kind of the flattish angle. Low and to the right. Low y coordinate, low sine value, that was 1/2. You could say 1/2 is not that low, but it's a lot lower than the x coordinate, the cosine value, which is root 3 over 2. Or you could get these from a table that you, or a big unit circle, or a quadrant of the unit circle, that a quarter of the unit circle that you've mind dumped on the back of your test. Anyway, these are known special values. Both the sine and the cosine of 45 degrees is root 2 over 2. Cosine, whoops. Again, this is cosine, this is sine, technically. Cosine of 45 degrees is root 2 over 2. Sine of 45 degrees is root 2 over 2 also. Now in red, the cosine of 30 degrees is root 3 over 2. And the sine of 30 degrees is 1/2. So you should write out these special values. Exactly. With a calculator, you might get decimal approximations, but we want the exact answer. This should be fair for a non-calculator part of an exam. Remember that fractions multiply across. What is root 2 times root 3? That is root 6. We get root 6 over, of course, 2 times 2 is 4, minus root 2 times 1 is root 2. 2 times 2 is 4 again. We have like fractions. We should combine these. We're combining like fractions. On the top, we have root 6 minus root 2 all over 4. Question: is root 6 minus root 2 equal to root 4? Is the difference of roots equal to the root of the difference? The answer? Generally no. And in this case, no, absolutely not. This is not 2. So that's wrong. Do not be tempted. That is not root 4 up there. I want you to simplify, but only in correct ways. That is incorrect. I'm going to erase all this. Leave this be. That's about as good as we can get it. Some books actually factor out a root 2 on top, but we're good with it. So then if you do that, you would get root 2 times the quantity. When you factor, you divide. We're back to, in fact, you could get it from here up here. Root 3 minus 1 all over the 4. Some books actually prefer that form. I will accept this form also, though. Root 6 minus root 2 all over 4. And if you have a calculator, you can do a decimal approximation for that. On some exams, you might be asked to give both an exact form and an approximation. Okay, do not go any further. Remember, root 6 minus root 2 is not root 4. So that's one way of getting an exact form, the exact value for sine of 15 degrees. But there's another way we can do this. What's another way that we can look at 15 degrees? Okay, we can think of it as a difference of a pair of special angles, like 45 degrees and then minus 30 degrees. But there's another way to look at this. 15 degrees. I'll type this out. $15 degrees is half of what?
Didn't get that.
Whoops.
Could you try again?
Oh, come on, we can get this. Please be quiet, Siri. Oh. So 15 degrees equals 1/2 of what? 30 degrees. Okay, 15 degrees is half of 30 degrees. Half of 30 degrees. We may be able to use a half angle identity. Okay, so sine of 15 degrees is sine of half of 30 degrees. So we can use a half angle identity where theta is 30 degrees. Using this identity over here, where theta is 30 degrees. So applying the identity, we get plus or minus the square root of 1 minus cosine of theta, which is twice the 15 degrees, right? So cosine of 30 degrees all over 2. And by the way, early on we can figure out, hey, the sine of 15 degrees, we know that 15 degrees is a quadrant 1 angle. So what sine, positive or negative, is this sine value? Well, in quadrant 1, we know that all trig values are positive. We know that we can take the positive root here, which means I can delete this, basically. What is the cosine of 30 degrees? We already figured that out in the previous method. Cosine of 30 degrees was root 3 over 2. But now we don't like the fact that we have a compound fraction in there. And also, we'd like to rationalize the denominator. So let's multiply by 2 over 2. We're multiplying by 1 here. When we do that, and we distribute through the top, 2 times 1 is 2, minus this fraction times 2 is root 3. All over 2 times 2 is 4. Again, we can delete the plus minus symbol at this point. We know that this will be positive. The sine of 15 degrees is positive. Okay, now down here, remember that we do have a rule for radicals. This does work. The square root of a over b, assuming these are both positive, is equal to the square root of a over the square root of b. The square root of 4 down there is going to be 2. Again, we can remove the plus minus, and we can get this as our final answer. So I'm claiming that this is another form for the sine of 15 degrees. Now you might be going, well, wait a minute, that doesn't look like what we got last time from method 1 when we applied a difference identity. Well, that could be okay. It's often the case, in trig especially, that you might get one form of the answer, your friend, or at least your study buddy, gets another form for the answer, and you could both be correct. In fact, on an exam, I would accept both of these responses. Some people might prefer this because you don't have the nested radicals, but if you come up with this on an exam, let's say, then I would accept this as well. In fact, these are equivalent. As an exercise for you, you might convince yourself that these are equivalent if you square this, and you'll find the squares are equal. And since you know that sine of 15 degrees is positive, that's a very good sign, literally. Okay. Take the square of this, take the square of this, show that those are equal, and that should be pretty convincing. All right, so we're going to do some more evaluating. We've evaluated sine of 15 degrees here, and simplifying in later videos.